This is the video number 2 in properties of fluids. Firstly, let's start with density of ideal gases. The one importante equation that explains the relation between pressure, temperature, and density, or specific volume, of a substance. It's called an equation of state. It is the ideal gas equation of state, where P is the absolute pressure, V is the specific volume, T is the thermodynamic, absolute temperature, ρ is the density, and R is the gas constant. The gas constant R is determined as this relation, such as R ρ is the universal gas constant. R and m is the molar mass, also called molecular weight. An ideal gas equation of state, number of moles N equals m per m. The ideal gas equation of state can also be written as this relation. An ideal gas at two different states are related to each other by this relation. The second part is talking about vapor pressure and cavitation. At a given pressure, the temperature at which a pure substance changes phase is called the saturation temperature. Likewise, at a given temperature, the pressure at which a pure substance changes phase is called the saturation pressure. The vapor pressure of a pure substance is defined as the pressure exerted by its vapor in phase equilibrium with its liquid at a given temperature. It is a property of the pure substance and turns out to be identical to the saturation pressure of the liquid. We must be careful not to confuse vapor pressure with partial pressure. Partial pressure is defined as the pressure of a gas or vapor in a mixture with other gases. For example, atmospheric air is a mixture of dry air and water vapor, and atmospheric pressure is the sum of the partial pressure of dry air and the partial pressure of water vapor. The partial pressure of water vapor constitutes a small fraction, usually under 3%, of the atmospheric pressure, since air is mostly nitrogen and oxygen. The partial pressure of a vapor must be less than or equal to the vapor pressure if there is no liquid present. However, when both vapor and liquid are present and the system is in phase equilibrium, the partial pressure of the vapor must equal the vapor pressure, and the system is said to be saturated. Our interest in vapor pressure is the possibility of the liquid pressure in liquid flow systems dropping below the vapor pressure at some locations and the resulting unplanned vaporization. For example, water at 10 degrees centigrade will flash into vapor and form bubbles at locations, such as the tip regions of impellers or suction sides of pumps, where the pressure drops below 1.23 kPa. The vapor bubbles, called cavitation bubbles since they form cavities in the liquid, collapse as they are swept away from the low-pressure regions, generating highly destructive, extremely high-pressure waves. This phenomenon, which is a common cause for drop in performance and even the erosion of impeller blades, is called cavitation, and it is an important consideration in the design of hydraulic turbines and pumps. Cavitation must be avoided, or at least minimized, in flow systems, since it reduces performance, generates annoying vibrations and noise, and causes damage to equipment. The pressure spikes resulting from the large number of bubbles collapsing near a solid surface over a long period of time may cause erosion, surface pitting, fatigue failure, and the eventual destruction of the components or machinery. The presence of cavitation in a flow system can be sensed by its characteristic tumbling sound.